Um, Good morning, good afternoon, everyone. Good evening for some of you. Welcome to the first edition of the GAWTEC webinar series on greenhouse gases and atmospheric composition measurements. I'm Valentina. I'm the YESS officer. And today we have with us Martin Steinbacher. I don't know if the pronunciation was correct. From EMPA in Switzerland. He will be giving a presentation on the importance of quality assurance and quality control for long-term in situ atmospheric composition observations. With us today, we have Sonia from GAWTEC, Claudia from GAW, and a YESS member as well, and Faten, she is a YESS member. So great that all of you can join us today. We have 84 people, a lot. Regarding the code of conduct, please be polite and respectful to the speakers and to all the participants today. You will be mute and you can't access to your video during the presentation. But if you have any question during the presentation, you can always leave your question in the chat box. So Martin will be replying the questions afterwards. We are recording all the contents of these webinars, the presentation, the chat box, and the webinar will be available in some days. Will be available in the YouTube channel of YESS, and also in our website. So if you miss some part, you can always watch it again. And after this webinar and the three other webinars of this series, an outcome report will be prepared and it will be published online in our website. So now I give the floor to, I think, Sonia. Claudia first.
Thank you, Valentina. Hello, everybody. Good morning, good evening, good afternoon. It's very exciting to see how many people from different parts of the world join us today. And I'm very happy to be here as well. And would like to briefly start with the fact that atmospheric composition matters to many important problems that society is facing today. They are somehow, many of them are related to atmospheric composition and its interaction with ecosystem, human health, weather, and climate. And you can see here some of the important problems that we have and that we will probably continue to have. And we only know about how these problems are evolving, whether they get better or worse, if we have long-term atmospheric composition measurements. And this is why we talk about this today. Within GAW, we measure 6 groups of variables: UV radiation, stratospheric ozone and the vertical ozone distribution, greenhouse gases, reactive gases, total atmospheric deposition, and aerosols. And in total, this is about 60 variables. The Global Atmosphere Watch program of the World Meteorological Organization provides international leadership in research and capacity development in atmospheric composition through the long-term systematic observations of chemical composition and related physical characteristics of the atmosphere, quality assurance and quality control, and co-designed products and services of relevance to users. And GAW built on the partnership involving contributors from 100 countries from all over the world. And I would like to take the opportunity to thank everybody who contributes to the GAW program. And we can see some examples of stations here, but this is of course not all of them. So thank you very much. GAW is currently in the middle of its implementation plan. And the vision for the next decade of GAW is to grow the international network of high quality atmospheric observations across local to global scales to drive high quality and impact science while co-producing a new generation of research-enabled products and services. And for all of this, we of course also need communication and capacity development. And related to capacity development and GAWTEC, I will now hand over to Sonja Böll, the GAWTEC coordinator. Thank you very much and enjoy the webinar.
Yeah, thank you, Claudia. I'd like to introduce the GAWTEC project to you. The Global Atmosphere Watch Training and Education Center, called GAWTEC, is part of the GAW Quality Assurance and Science Activity Center in Germany and responsible for training and education of global and regional station personnel. The aim is to meet the GAW data quality objectives. The courses are held twice a year for 2 weeks, and the topics include aerosols, UV radiation, reactive gases, precipitation chemistry, greenhouse gases, and data evaluation. GAWTEC is financed by the German Environment Agency, the Bavarian State Ministry of the Environment and Consumer Production, and the World Meteorological Organization. Next slide, please. Yes, since 2001, over 400 participants from 80 different countries have visited and were trained at the training center at the Environmental Research Station Schneeferner Haus, which you can also see in my background. And the station is on Germany's highest mountain called Zugspitze. For more information, you can also visit our website. It's gawtec.de. I think I will hand on to Phaeton.
Thank you very much, Sonia. Hello, everyone. It is so exciting and so lovely to see you for the first edition of GAWTEC webinar series on greenhouse gases and atmospheric composition measurement, which is a joint event between YESS community and Global Atmospheric Watch GAW program of the World Meteorological Organization, WMO. So thank you very much for joining us. Thank you, Sonia, for the next presentation of GAWTEC, Claudia for introducing GAW. I'm Steinbacher, YESS Executive Committee member, and I'm glad today to give the presentation about YESS Community, which is a network of early career scientists who are representing the world. We are unifying international multidisciplinary early career research in a powerful network and providing a voice and leverage for a better future to serve the society. YESS has been officially endorsed by World Weather Research Program, WWRP, and World Climate Research Program, WCRP, the research arm of World Meteorological Organization, and we have close relationship with GAW. YESS has several representation in international initiative and communities and organizations such as the Research Board of WMO, Future Earth, and etc. As you can see there, in YESS structure, we have the YESS community and we have the YESS Council, the working group, the executive committee, and the regional representative. We have 4 working groups. We have the membership working group, the science, the outreach, and the online working group who is hosting this webinar session today. And we have the regional representative and the executive committee, which we vote for them every year. It's usually between March and April. Our active members from working group and from regional representative can join YESS Council at any time. So there is the website, and there we share with you all our social media. So if you have any question or inquiries, you can please contact us, and there we have our email address. And thank you for your attention now. Thank you for joining. And I hand over to my colleague Sonia to introduce the speaker of today. So thank you very much.
Yes, our speaker today is Dr. Martin Steinbacher. He's a senior scientist at the EMPA Laboratory for Air Pollution and Environmental Technology in Switzerland. His main duties are he's a principal operator of the Swiss National Air Pollution Monitoring Network's air quality observations at the high altitude research station Jungfraujoch. He's also the manager of the Quality Assurance and Science Activity Center in Switzerland in support of the WMO's Global Atmosphere Watch program. And he has also been speaker at former GAWTEC courses. We are very happy that you're here today, Martin. I'd like to encourage participants to ask their questions in the chat box, and we can answer it after the presentation. Yes, Martin, the stage is yours.
Okay, thank you. Let me share my screen. Do we see it? Yes, okay. Here we are. You can see it? Okay. Thank you, Sonja, for the nice introduction. Thank you, the GAWTEC team. Thank you, the YESS community. Thank you, the GAW Secretariat in Geneva, for organizing this webinar. I'm very pleased to be the first to give the opening lecture of the first webinar of its kind, of the first GAWTEC webinar. Since it is the opening lecture, time is limited and the audience is most likely also pretty diverse. I do not want to go in too much detail, but I want to talk about quality assurance and quality control, things you have to consider when you want to do long-term atmospheric composition observations. And I split my talk in 3 parts. First, I want to talk about the design and station setup, because achieving decent quality of your observations, you need to start already in the preparation of your measurements. Then once everything is set up, I will talk in my second part about the instrumentation and operation, what's going on in the station. And the third part is the data management and data processing part. This can take either place at the station or somewhere centrally at the headquarters or in the data processing unit. I think I can mostly skip that since Sonja mentioned that already. I'm a meteorologist by training and have a PhD in atmospheric chemistry, and currently I'm the principal investigator of the majority of the measurements at the GAW station Jungfraujoch. I'm working for the Quality Assurance Science Activity Center Switzerland, and I'm also chairman of the Atmospheric Monitoring Station Assembly of the European Integrated Carbon Observation System. For the ones that do not know Jungfraujoch, that's also a high altitude station at 3,500 meters above sea level in the Swiss Alps. It's part of the Swiss National Air Pollution Monitoring Network that is run by EMPA in collaboration with the Federal Office for the Environment. And as I said, it's also part of international networks like the ICOS network that is focusing on harmonized greenhouse gas measurements across Europe. And Jungfraujoch is also one of the 32 global GAW stations that we can see here that are pretty much distributed all over the globe. And my second duty is the Quality Assurance Science Activity Center Switzerland task, where I'm mainly in charge of supporting stations in data sparse regions. Since in Europe and let's say in the Northern America, there's a very good coverage of air quality monitoring stations, but in some areas of the world, very important data is lacking. And that's why we try to support. Here we see some photos from stations in Vietnam, Indonesia, Kenya, and Chile, for example. And how do we support these stations? It's sometimes we provide instrumentation, but most of our duties are training. Here we see quite some impressions of training activities, either on-site. Sometimes we have also technicians in Switzerland for training. And this year, since travel restrictions apply, there are more and more also virtual events like today or another. That's a photo of an event we had a month ago with Indonesian colleagues. And Sonja mentioned the GAWTEC courses already. EMPA is for about 15 years a long-term partner of the GAWTEC program and is involved in teaching, especially when it is about greenhouse gases and reactive gases. And training capacity building is an important part of QSAC, and I also would like to mention Meteor Swiss here, acknowledge Meteor Swiss for funding of QSAC Switzerland. Okay, let's start with the first of the three topics, design and setup. Some very basic questions you may ask yourself before starting to set up your instrumentation is, why do I want to measure, or why do I need to measure at all? That brings you immediately to the second question: which compounds are of interest? Am I interested in gaseous compounds, greenhouse gases, classical air pollutants, in particles, dry or wet deposition? Do I want to make meteorological measurements? Yes or no? Then where are the measurements reasonable? Do I want to measure upwind, downwind of a specific pollution source? When we talk about GAW, which is traditionally at least more kind of a background measuring network, GAW tries to find sampling sites with the best possible representativeness. That means usually background sites that are representative for a large area. That's why usually you want to avoid sampling some local effects, sources or sinks. Then what kind of data time series are needed? There you can think of quite different approaches. Let's say satellites that screen the whole atmosphere. You can have ground-based remote sensing instruments that look into the sun, that can also measure the whole atmospheric column. You can have mobile measurements on drones, on balloons, on airplanes. You can have towers, fixed stations, and so forth. And then you can also think about, do I need continuous measurements? Do I need only spot sampling? This is an example from flasks taken twice a month at the station in Indonesia, Bukit Kota Tabang, from the NOAA flask sampling network. They have a flask sampling network all around the globe, 50 or 60 stations. And with their 2 samples per month, this is now time series from 2004 to 2011, 7 years. You can see nicely the increase in CO2 as expected, as we can also see at other stations, and some seasonality in methane that has to do with this rainfall patterns. But in 2010, we installed a continuous CO2 analyzer there, and if we compare the measurements there, this is now a 10-day period in May 2010. And in the red dots are the 2 flasks that are taken in that episode. And you see we get a very good match, but we can learn other things here when we have the high quality observations. The long-term flask observations are a very cost-efficient way to measure, well, to learn something about the global trends. If you have a global network of these flask sampling networks, usually the flasks are taken on site and are sent then to a central laboratory, in this case to Boulder, Colorado. But if we use continuous high precision analyzers, we can also learn something. We see these diurnal cycles, that's the uptake due to the uptake by the vegetation during daytime and the release of CO2 during nighttime. And then for sure, this is a much more costly approach because these analyzers are not very cheap. But well, this is what I want to say here with that example, that you have to make up your mind before what do you need, what you want, and then you can choose your approach accordingly. And when is the right time to measure, especially when you do this flash sampling? Do I want to sample every week at the same time of the day, or do I want to sample only once a month, but then five samples in the course of the day to learn something about the diurnal cycle? Do I just want to sample, take air samples during biomass burning episodes, whatever monsoon periods, and things like that? Here I would just want to mainly focus on the ground-based in situ observations. This is also my main expertise, and this is also I think the most straightforward approach. Well, to start, very basic infrastructure requirements. What do we need? You need a shelter. You need a reliable power supply. In most of the world regions, you need also an air conditioning. All these instruments produce quite a lot of heat. Even if it's not too hot outside in a little shelter, it will become pretty warm after some time. You need internet access for data transmission, and usually also for remote access in case something is not working as expected. And you need some mast for free exposure of the inlet. I will talk about the different reports that are available for where you can find useful information in a couple of minutes. But here you see a quote from the ozone measurement guidelines that say that laboratory building and inlet location should be best set upwind of any local source that may contaminate or interfere with your sampling. And this sounds more trivial than it is, because sometimes we see also inlets like that, because there's this is a photo where the orange little thing, that's the inlet, and you see there's just a tube was put outside of the window about 50 centimeters out next to the wall of the measurement shelter, and that was for ozone measurements. It is, well, that's definitely not perfect, because also it's depending on the wind direction, it will be in the lee of the hut, and also if the inlet is too close to the walls, especially when you think of ozone. Ozone is very reactive. It can deposit on any surface. You may have a loss of ozone when you measure at this sampling site. And then we also changed the position here to the top on top of the roof. See, that's maybe not very good. Well, that's a bad example, and something you also need to consider, especially when you want to measure CO2, because CO2 heavily interacts with the vegetation. If you measure it heavily vegetated in a heavily vegetated environment, you should usually be well above the canopy, because as I said, during daytime, the vegetation takes up CO2 and releases CO2 in the nighttime. That's why often there are kind of tall towers used, and the air is drawn from the top of the tower into the shelter. You see somewhere a bit hidden between the bushes down there. Well, sounds also trivial, access to the stations 365 days a year, but we have seen that this is, well, think of mountain stations like the Jungfraujoch. Luckily there we have an underground drain going up there, and access is always possible. But in other regions you have monsoon, you have landslides, things like that. If something fails and you have no access to the station, this will cause some troubles, or will lead to some longer data gaps. And either make sure that you have somebody on site very frequently, or some local support. Sometimes it's just to push a button to reboot the computer, something like that. It's very helpful to have somebody very close by who could do at least some very basic maintenance. And once the infrastructure is set, you need instruments in periphery. And again, we experience, when we support stations all over the world, that often money is available for the analyzer, but the other bullets are often kind of forgotten. You need some periphery for automatic calibrations. You need some valves that switch back and forth. You need a reference gas for calibration. You need pressure reducers that you can screw on your regulators. You need plumbing. You need tubing. You need connectors. Some rain protection for your inlet. Maybe a drying unit. And once all that is in place, you need also a running budget for consumables, spare parts, backup instruments, etc. Okay, let's assume that the infrastructure is set. We go to the next step. We try to accommodate our hut, install our equipment. And then the first question that comes into play is which instrumentation to use. But before I want to do that, I go one step back and I show a sketch from the GAW Implementation Plan that was already mentioned by Claudia that illustrates the GAW quality management framework. And I'm always pleased to show that, because here we nicely see that the quality assurance science activity centers and the world calibration centers, EMPA is also hosting one of the calibration centers, is right in the center of that quality management framework. You have the GAW stations at the bottom, and you have central calibration laboratories that produce reference gases. Stations can purchase them, and then finally data end up in the World Data Center. And there are scientific advisory groups that kind of oversee the overall performance. And there are also some expert groups that are even not shown here, or quite a number of expert groups that also advise or set a bit the guidelines for the observations. And one of these expert teams, or the expert community in this case, let's say, is the GHMT, the Greenhouse Gas and Measurement Techniques community that meets every second year and produces a meeting report afterwards. And here you see the table that shows the recommended network compatibility goals for the main greenhouse gases. And there we see, for example, for CO2 in the Northern Hemisphere, we try to achieve a network compatibility goal of 0.1 ppm. In the Southern Hemisphere, it's even more demanding by 0.05 ppm. This network compatibility goal is defined as the maximum, the scientifically determined maximum bias that can be accepted without jeopardizing, let's say, flux inversions, determination of source strengths of different greenhouse gases. And when you may know that the constant atmospheric concentration of CO2 in the atmosphere is about 400 ppm. The network compatibility goal is 0.1 ppm. That means that's a less than a per mil. That's a quarter of a per mil. And why is that the case? When we look at some data compilations made by the World Data Center for Greenhouse Gases in Japan, we see here in latitudinal slices the CO2 increase over the last 30 years. And we see nicely this yearly wiggles when in summer CO2 is mainly taken up by the atmosphere, while it is there's a net release in winter and in early spring. And it is not very well seen on the Southern Hemisphere because there's less of land mass and less biosphere that can do that. And when we take all these red lines from the left figure, we can plot that in one consolidated plot. We see that there's a north-south gradient, but the north-south gradient is pretty small. And from west to east, it's even smaller. And that's why we need to be very precise with our measurements to allow for sound, for robust changes, spatial gradients in the CO2 concentrations that are required to learn more about the sources and things. And that's why the requirements in terms of precision are so demanding. You may, as a take-home message, you may recall that there's a 1/4 per mil precision that we try to achieve with the CO2 measurements. And then that's also another figure. This is actually the basis for the plot we have seen before. These are all stations that report data to the World Data Center for Greenhouse Gases from the top, from Alert in Northern Canada to South Pole at the bottom. And the color code is the CO2 increase over the last, that's now 50 years already. The red line shows the equator. That also illustrates that there's much less time series available on the southern hemisphere than in the northern hemisphere. And but you see the gradient is pretty small here. That's a paragraph that comes next to this table we have seen before with the 0.1 ppm. And well, it says that to achieve the required level of network compatibility, it's important to understand and carefully consider the design of the whole analysis system. This is what I tried to mention before. Interestingly, well, no single instrument type is recommended because many can be used and none are foolproof. For sure, there are instruments out there that perform better than others and they're more precise than others. But maybe even the most advanced ones now are, it's maybe even too appealing to just put it out there, plug and play. They spit out some numbers, but without decent quality control and quality assurance, they won't produce the data of the best possible quality. And finally, the last sentence reads here: a trade-off in instrument stability and complexity versus cost must often be balanced according to the needs, resources, and challenges of the measurement program. That means even if you have there may be very high-end instrumentation that is not too robust, and if it sits somewhere at a very remote place where access is very difficult, maybe a better choice to take something more robust that is maybe a little bit less precise, but it can maybe produce a data with a much better data coverage. For CO2, it is rather straightforward, let's say, but that's an example here for tropospheric ozone, where the data quality objectives are more tricky to define. That's a paper by David Tarasik from the Tropospheric Ozone Assessment Report that was published last year. That we see on the leftmost column, we see the scientific task or question: long-term tropospheric ozone monitoring, air quality model validation, and whatsoever. And the second column here reads the goals and requirements. And that means depending on your scientific question, the requirements will be different. For long-term monitoring, it is about 1 nanomole per mole or 1 ppb. For air quality models, there are different requirements: chemical data assimilation, satellite validation, and so forth. That brings me back to one of my first slides where I said, before you start or before you purchase your instrumentation and you think about your measurement setup and your periphery, you should define your main scientific aim, and depending on that, you have to choose the instrumentation and your whole setup. Okay, I mentioned some of these reports already before, the implementation plan. I also mentioned that the different experts groups that are existing, and they produce quite some GAW reports. There's some experts workshop, have been some experts workshop on NOx, ozone guidelines, GHMT reports, aerosol measurement procedures, guidelines, recommendations, and there are many others. At the very end, you will find the web page where you can browse all these reports. In addition to that, there are other project reports, web pages. ICOS was mentioned before, the European Integrated Carbon Observation System. There we compiled a very comprehensive specifications document what we need and how we want to measure the CO2, methane, and nitrous oxides, for example, to the best possible degree. The NOAA page gives quite some useful information how they do their CO2 measurements in Mauna Loa, one of the most known time series at all. Then environmental agencies, European Committee for Standardization, there are also quite some reports out there that provide some useful information about techniques that can be used. They give some recommendations where you can learn a lot before you really start and purchase your equipment. Scientific publications, plenty. There are just a couple of a few examples about data processing, ozone particles, CO2 and nitrous oxides techniques, consultation of peers, talk to your colleagues, go to conferences, have a chat with people that do similar observations also in similar environments as you want to do. And again, don't forget the periphery. It's not only the instrumentation, the instrument itself, the analyzer that you need, but you also need the periphery for calibration and quality control. Traceability and calibration. That's again the example for CO2. I mentioned the central calibration laboratories before. That's for the greenhouse gases. This is NOAA in Boulder, Colorado. And they maintain a suite of 15 primary standards where they very precisely determine the CO2 concentration in it. And then they have a set of secondary standards where they determine the concentrations in comparison to these primary standards. And then they have another level of hierarchy of standards. And one set here is called outside the carbon cycle group researchers, and this one can be purchased by station operators, and these will become then the primary laboratory standards. And usually, especially when you have a network of several stations, these standards are rather costly. Usually, you keep a set of those standards in your labs, in the central lab somewhere. You assign numbers to another level of standards, and these are the standards that you use for daily or for regular calibrations, let's say. And then again, that's a sketch from the ICOS group. You have the air inlets here somewhere, and then you need something, a valve that can choose automatically if you want to sample air or one of these calibration tanks for quality control. Now, all that is in place. You want to know how often you need to calibrate. Okay, maybe I can skip that due to the interest of time. But then we are here. How often do you want to calibrate? And for the newest generation of high precision analyzers that are usually also very fast, it is common to do kind of Allen variance tests. You just measure one tank for, in this case, more than 400 hours, let's say 10 days. And at the lower panels, you see the Allen deviation. That's the standard deviation. If in a perfect world, this line should come more and more down because you have more and more data for averaging, and then the standard deviation would become smaller and smaller. But since there's drifts in the instrument, even if it's very, very little, usually you find a minimum where it's the best performance achieved. And here a paper by a colleague of mine, Christoph Zellweger, based on these plots, we state here that approximately every 30 hours, this cavity enhanced laser spectrometer we used here should be calibrated. That was a laboratory test, and then in the field you can also gain quite some experience. This is again from the ICOS network for 1 year calibration, 4 different calibration gases for 1 year. There was a change in the calibration tanks here in summer 2018. Here you see kind of the drift of the instrumentation. This is the difference of the measured value to the assigned value. That means the analyzer measures about 1 to 2 ppb higher than the reality. But if you know that and you track that, you can easily correct for this. And here calibrations are only taking place every 2 to 3 weeks. But in addition, there are some target measurements done. A target gas is we see here in the lower panel. In the upper panel, we see again 3 calibration gases measured every 5th day. And in addition to that, we have a target tank that is measured at least once a day for rapid detection of some instrumental artifacts. Because if you calibrate here every 5th day, or in the ICOS example, only every 2nd week, you will only realize after 10 days or 2-3 weeks that there was something going wrong. And if you have one reference tank that is measured very frequently, this can be of lower quality, because it is just, you just want to track that the signal is stable over time, and the calibration function that you apply to the data is doing its job. Then the data should be on a straight line here. And to do all that, you also need some appropriate data processing software. CO2 was again rather an easy case when we look at other gases like ozone. Ozone is a very reactive gas I mentioned before. Cannot be stored in high pressure cylinders because it will vanish immediately. For ozone, it's different. There, the reference is not a suite of calibration tanks like we had at NOAA, but they are standard reference photometers, all built by the National Institute for Science and Technology in the US. And there are about 60 of these NISTs out there, and they maintain the reference for GAW. And these 60 instruments, the SRP family, is undergoing regular key comparisons organized by the BIPM in Paris, and there we ensure that all these reference photometers measure the same. And then when you want to calibrate your ozone instrument in the field, usually you need a standard, a transfer standard that is compared to one of these reference photometers. This is here a schematic from the World Calibration Center run at EMPA. And then we use the transfer standards. We bring it to the station, and we make a comparison there. And this is what the World Calibration Center EMPA does with that regular audits for now maybe 20 years. And there you see that we visited already quite some stations all around the world doing these calibrations. But usually measurement networks with having its own transfer standards and have access to the standard of reference photometers can do exactly the same. Okay, last part, data management and data processing. Once the measurements are done, you need to process this data. You should start with an overall concept. How do you get the data from your instrument to a central computer on site usually? How can you transfer the data, preferably automatically, to another server where people that process the data can access it? You have to think of the backing up the data. data visualization, preferably on-site already for the operators, that they can go through the data of since the last visit easily, and then finally you can make that data available at the World Data Centers, for example. And this is a nice sketch from Lynn Hassan, also from the ICOS network, that I like quite a lot. That shows that usually you start with raw data, you do some automatic filtering. Let's say you also record the instrument pressure, the temperature of the measurement cell or whatever. You do some flagging, and then you have to split these data in your when calibration gas was measured, when ambient air was measured, and when these target data were measured. And then you need to filter, you need to account for the stabilization, and then these calibration data need again to be applied to the in-situ data and the target data. This we can see, for example, here. This is, we started to measure ambient air, and then we switched from air to port 2, port 4, port 5, 6, 8, and back to air. It means we measured 5 different high pressure cylinder, reference gases. And then you see the red data are the ones that are rejected, because then it usually takes some time after switching the valve. It takes some time till the signal is stabilizing, and then only the second part is used for determining the reading of the instrument when a gas that was connected to port 6, let's say, was measured. And you need to record, along with the concentrations of your analyzer, you also need to report the valve position, that you know at which point in time which reference source was measured, or if ambient air was measured. And all that is usually it urgently calls for some automated software and no spreadsheet solution. Well, this is what I said here. Automated processes are encouraged, facilitates diagnostic and quality control, and also allows for rather easy reprocessing of the data. Like I said, NOAA hosts a suite of calibration gases, and sometimes they need new suites because they also run out, and their scale changes, and then stations are asked for reprocessing of all their data, and then it is really helpful when these things were done kind of automatic, with some automatic procedures. Estimation of measurement uncertainty. Some people say that data without uncertainty are useless. That's, well, this is maybe a webinar of its own, measurement uncertainty, but just to give you a little short flavor, there's a guide to the expression of uncertainty in measurements, GUM, again, available via the BIPM. That is, well, for an atmospheric scientist, that's sometimes a difficult read, but it's very useful to also look into these documents once to learn a lot how this can be done. And in the ozone measurement guidelines mentioned before, we did that in 2013. There we had a couple of issues we identified, like drifts, span drift, zero drift, repeatability, influence of change in temperature, pressure, water vapor interferences. And then we had some best guesses, some expert judgments. Sometimes you can run some tests to quantify the effect. And then we came up with the equation we can see here. that determines the uncertainty of your ozone measurements depending on the concentration. And luckily we could also prove that with some experimental data. This is again from the Swiss National Air Pollution Monitoring Network that I mentioned before. Here we see the intercept versus slope. There you can imagine that we make scatter plots of the measured values versus the assigned values, and then if you get some intercept slope pairs and you apply the equation we can see on the left, all data should, or 95% of the data should lie within this gray shaded area. And there we see that this was very well confirmed by real measurements, real calibrations, that the estimated uncertainty we determined in that report definitely makes sense. Okay, time is running up. Very briefly, the GAW program also recommends the adoption and use of internally accepted methods and vocabulary, that everybody uses the same vocabulary when talking about the same things. There's the WIM, the International Vocabulary of Metrology, rather lengthy, difficult to read, let's say, but we, the QSX Switzerland, some years ago, and we regularly update that, produced a glossary that can be found at our webpage. That is a chosen subset of the vocabulary in the BIPM report, and also illustrates or explains some of the terms with some GAW specific examples. Okay, data management. On site, I mentioned that data visualization is important. That this is now a screenshot of a setup in one of the stations we supported in Vietnam. There you can see the time series. You can easily switch back and forth. You can go back in time to see how the data looking like yesterday. It's more than just checking the little display on the instrument instantaneously. Then there we have a logbook for data management, very important. And then at the central data processing unit, you need other tools that can at least semi-automatically split the data, as I mentioned before. And there you can have some more sophisticated solutions like this one. That was something where we had also some automatic filtering inside, or you can also just use some script language that is maybe less visualizing the data, but if you know what you do, that also does a very, very good, decent job. Okay, well, that's actually trivial. You should document everything you do. You can use a very simple notebook to write that down. You can also use pen and paper, but make sure that you make backups, photocopies or whatever, and preferably for sure you have that in a digital form that you can also transfer that on other computers. And there are also other more advanced versions for free. This is called eLog, where you can predefine some categories like the author, the type, which instrument your logbook entry is referring to, and then you have already some of the basic information selected just by using these pull down menus. But checklists is also trivial. Usually have some checklists, or prepare your own checklists, what to do every week, every month, every 6 months, and then, well, just step by step we prepared some step-by-step explanation how to do that, and this is very helpful that nothing becomes forgotten. Regular updates and courses, GAW Station and Information System, that's the metadata repository where all metadata should be easily found, because Claudia mentioned the 6 focal areas of GAW, and there are also 5 or 6 different data centers. But here you should find that that should be the place where you can find all information, which data is available where, and also data responsible persons are listed here. But for sure, these kind of things need to be updated regularly by the station operators themselves. I think that's the last thing. Additional quality control. Try to participate in comparisons like round-robin exercises. Within GAW, there are different round-robin exercises that are ongoing again and again. That will help for comparison if your data are sound, are accurate. And then a very easy thing is just compare your data with data from other similar stations. And for illustration, I show again that CO2 north-south gradient. If you measure something that would be labeled in blue, like say let's say 360 parts per million in 2010, then you would easily see that something is most likely going wrong with your measurements. And there are also many online tools available in the web for trajectory calculations. This is very helpful for data interpretation, where you can kind of get an easy feeling where your air masses were coming from when you sampled. This is especially of interest when you have, let's say, I think that's for a station in South Korea on Jeju Island, where usually you measure clean air when it comes from the ocean. But if the wind is turning and air mass come from the continent, you may see some elevated concentrations. And this is some easy visual support, and when you want to interpret your data, if specific peaks in your time series can be real or could be likely measurement artifacts. Okay, let's conclude. You have seen similar thing already before. This is what you need in terms of infrastructure. This is what you need in terms of instruments and periphery. And that's a sketch we prepared some years ago that shows if you want to measure, you do not only need the blue analyzer in the shelter here, but you need also the reddish calibration facilities, computers, that to produce decent data that can be sent to the central data repositories. And before you start, you should clearly define why you want to do that. This will help you identifying the data quality objectives. Once you know how precise you want to be, you can find the suitable instrumentation. Then you should design your operation calibration strategy, prepare some standard operation procedures, checklists, troubleshooting strategies. How can you fix problems once they will appear? For the data, you need a robust data management. And well, that's all for sure is involving costs. You should have a sustainable budget because, as I said, can be rather costly, and you need to support. You have to have some convincing arguments that you get decent support from your funding agency. Okay, I will stop here. These are some of the references of the resources I have shown before. And I would like to thank you out there for your attention.
So thank you, Martin, for your presentation. We collected some questions in the chat box, and I'd like to read out the first one. What is the minimum data period that can be used to obtain a trend or perform trend analysis?
Yeah. Well, if you have two measurement points, you can draw a line and then you have a trend. You measure once in 2010 and once in 2020, and then in theory, you could determine a trend. But well, the real answer is, well, it depends on the trend, on the strength of the trend, on the precision of your analyzer. For ozone, for example, it's about 10 years, let's say, I would say. And CO2, we have a very significant trend of about 2 ppm per year, but then you have every year you have these wiggles up and down due to the biosphere that are on the order of, well, depending on the station, on the order of 15 to 20 ppm. Well, then you for sure then you can do some calculate the annual, you deseasonalize your data, but also there you need a couple of years of data. It's different. It depends on the parameter, on the trend, and on the precision of your instrument.
Thank you very much for the presentation and for answering the questions, Martin. The next question is, for example, for calibration of a thermal analyzer of SO2 using a gas tank, what is the suitable period of calibrating the SO2 to be stabilized with time?
Okay, well, we do that every couple of days. And finally, if you do that every day or every second or every third day, it doesn't change much, because once you do that so frequently, you do not want to do that manually. That means you need some valve, some calibration box that can do that automatically, or you can set a programmable box that can switch automatically between calibration gas and ambient air. And then it doesn't matter if you do that once a day or every second day. It is more a matter of calibration gas that you need. And usually we suggest to start more frequently, and then after a couple of months you see if there's no real change in the instrument sensitivity. In a perfect world, the instrument sensitivity does not change at all, and then you do not need to calibrate. But for sure, it depends on changes of atmospheric pressure in the instrument, temperature in the lab, temperature in the instrument, whatever. Some dirt on the inlet filter. Well, there are thousands of reasons why instrument sensitivity can change, and instrument sensitivity does change. And that's why usually, to be on the safe side, you do it even more often than it is even needed. Every couple of days, let's say.
Thank you very much for the presentation, Martin, and for answering the question. We have a third question, which is saying how to deseasonalize the data. Are there any ready-made tool available for performance trend analysis? If the measurements are not part of the GAW network, can we get support for quality controlling?
Well, yes, there are algorithms out there. Usually I do most of the data analysis with R. It's kind of a little bit similar to MATLAB, but R is even for free, open source. And there, at least there, I know it best. There are many packages that are also freely available. You can download. You can go to the CRAN, Comprehensive R Archive Network, and there you can search for whatever whatever buzzwords. It's, yeah, well, and well, there are several approaches out there that are freely available. Usually a good thing is to also check again the literature, and usually if the paper is well documented, it's usually, even the function is maybe sometimes mentioned, or at least it refers to a specific package of a software tool that can do that. That has nothing really to do with GAW. That's kind of a basic problem that was already targeted thousands of times.
Thank you. The next question is, does frequent calibration mean frequent instrument adjustment?
That's a good one. No, it doesn't mean that. If I have a whole day to teach, usually I show some examples. It is even not recommended to adjust the instrument parameters every time. We rather suggest to track the sensitivity, and the sensitivity changes with time, and then you can fit some low pass filter, let's say, through the background signal of the instrument, or when you apply a specific concentration, because often it goes a little bit up, then it goes a little bit down. And if you change and you can easily correct for that afterwards with some suitable tools. If you change the settings every time, you will get some steps in your time series, and then if you want to correct afterwards, you have to do that slice-wise for every time you change the parameters really on the hardware. We do not recommend that at all.
Thank you very much, Martin. We have another question coming from Noah. And the question is saying, if we have a long-term site setup, MT Bachelor in Oregon, United States, where we are measuring the O3 and the suit of another compound since 2004, how might we become a part of the GAW network?
Okay, well, that's more a question to Claudia. But the short one is you visit the WMO webpage, and there's an application form. And I don't know, Claudia, if you want to add something to that. Usually there are requirements. Usually there are requirements in terms of data release, at least once a year or 6 months after having made the measurements. I don't know, Claudia, you want to add something to that?
Yes, I think that's pretty much summarized it. There's instructions on the website which explains very well what needs to be submitted. I will post the website in the chat in a moment. And then you submit an application, and then it will be evaluated by the scientific advisory groups. And then you will hear back. So that is the way you can join. The data has to be made available to the World Data Centers. So that would be an important part of it. And there are some other requirements that I think it's easiest if I post the link in the chat. Just give me one moment. Thank you. And it's a very good idea to become part of the GAW network.
Yeah, maybe we can take the last one. And the last one is saying, are there metrics to evaluate the instrument sensitivity?
Well, you take a reference gas, and you know there's 414.5 ppm of CO2 in it, and your instrument measures only 412.7 ppm, then you know that you are 2.2 or whatever, 2.2 ppm off. And then you, well, in very easy words, well, you do that with several calibration tanks usually, And then you can determine a calibration function, and then you correct for that. Is that, well, I think, well, that's the fast answer, let's say, at least. And the more calibration gas you have, usually the calibration gases should span the whole range of atmospheric concentrations you observe. Sometimes sensors are non-linear, then it becomes kind of more tricky, but this can be also investigated when applying several calibration gases of known concentration.
Thank you, Martin, for the great talk, and thank you all attendees for the fruitful discussion and the great questions. I give the floor to my colleague Valentina to close the session now and make the announcement of the next webinar. Thank you.
Thank you, Faten. Thank you, Martin, for your presentation. I think a lot of people had great questions, so I'm happy to see everyone asking in the chat box. So now I want to present you the next webinar. Will be next week, next Monday, December 14th, at the same time as this one, 2 p.m. UTC. I'm copying the link if you want to register in the chat box. We also make the proper announcement in YESS social media. And the speaker will be Andrea Kaiser-Weiss. She will be talking about modeling of air masses, impacts of Corona lockdown. So you are more than welcome to join us next week. Well, see you in 1 week. And thank you again, Martin, for your time and your great presentation. And if you have any other questions to all the attendees, you can reach us. And I think that's it. Have a great night or a great afternoon or day, depends on which part of the world you are. Bye, everyone.
Okay, thank you. Bye.
Bye. Thank you all. Bye-bye.